Hey everyone, today we're going to be continuing learning about exponential functions. We're going to be specifically writing exponential functions from situations, and we're going to continue to talk about exponential growth and exponential decay. So, with exponential growth, remember that our b value has to be greater than 1. Our common factor has to be greater than 1. So when we're reading a problem that talks about percent growth, um, we're going to have a rate of growth, and that's going to be R. And then our formula for exponential growth is going to be Y equals A times 1 plus R raised to the X power. So remember, A is our starting amount. And then R is going to be our rate of growth written as a decimal. Okay, so like 25% would be 0.25. So let's look at an example. Let's say a colony of bacteria grows 25% per hour. It started with 100 bacteria. All right. So to write this exponential growth, we have a rate of growth that's 25%. So R as a decimal is going to be 0.25. We started with 100 bacteria. So we're going to have the equation y equals 100 times 1 plus 0.25 raised to the x power, which is y equals 100 times 1.25 to the x power. So we're adding that to 1 because without the 1, it would be less than 1, and then that would be decay. So we have to add the 1, that's 100%, and then it's growing by 25%, so that's 1.25 raised to the x power. Okay, compound interest is a special type of exponential growth, and it has its own formula. So the formula for compound interest is A equals P times 1 plus R over N to the NT power. All right. So A is the account value. P is the initial principal. R is the annual rate. N is the number of compounding periods per year. And T is the time in years. All right. So a lot of different values, but they still mean the same thing that we already know. The only thing that's different is now we're dividing our annual rate by a number of compounding periods, and then multiplying that number of compounding periods times the number of years. Um, A is still going to be your Y value, P is still going to be your initial value. We're doing the 1 plus R like we did with exponential growth, but now it's 1 plus R over N, and then it's raised to the NT power. So let's say a savings account earns 5% per year, compounded quarterly. And then the initial investment was $2,000. All right. So we can write an equation here. The account value is going to be equal to the initial investment, which was 2,500, times 1 plus 5% per year is 0.05. Compounded quarterly, that means 4 times in 1 year. So that's divided by 4, and then raised to the 4t power, or t is our number of years. Okay. And then exponential decay. Well, if we have a rate of decay, so remember for exponential decay that our common factor is between 0 and 1. And so we're going to have a rate of decay. It's also r. But with exponential decay, we're not going to be adding that to 1. We're going to be subtracting it from 1. And that's going to get us between 0 and 1. So again, A is our starting value, R is our rate of decay written as a decimal, and it's raised to the x power. So something that could decay, the amount of water in a pool drains 10% per hour the pool started with 10,000 gallons. I don't know if that's a lot or a little for a pool. I guess it depends on the size of the pool. But for this problem, 10,000 gallons. All right, so y is going to equal our initial amount, which was 10,000. Oh no, I did 100,000. 10,000 times 1 minus our rate of decay. Draining, it's going down. So that's 1 minus 0.10 raised to the x power, which is going to be y equals 10,000 times 0.9 to the x power. All right. And whoever's draining that pool, they're never going to have an empty pool because of that asymptote at y equals 0. All right. Number 1, the value of a house increased by 6% per year since 2014. In 2014, the house was purchased for $300,000. Write an exponential function representing the value of the house t years since 2014. So we have an initial value, which is 300,000. We have 6% growth. So R is going to be 0.06 as a decimal. So then our equation is going to be y equals 300,000 times 1 plus 0.06 raised to the t power, because it said t years since 2014. And then simplifying that times 1.06 t. Pretty simple stuff. All right. Number 2, you invest $5,000 into a HYSA. That's a high yield savings account that earns 4% interest per year, compounded daily. Write a function to represent your investment. So y equals our initial amount, which is 5,000, 4% per year. So R is going to be 0.04. So we have 1 plus 0.04 divided by compounded daily. There's 365 days in a year. So this is 365 days raised to the 365 t power. All right. What you will notice the more that you work with compound interest is you want an account that's going to compound it more often. So compounding daily is better than compounding quarterly. Compounding monthly would be somewhere in between. And then there's actually continuously compounded, which most accounts do nowadays. Continuously compounded is going to be the most efficient. We don't really learn about continuous compounding in this class, though. All right. How much money will your investment be worth after 10 years? So all I have to do is take t and replace it with 10 years to the 365 times 10 power. And calculator to calculate that. So I have 5,000 times 1 plus 0.04 divided by 365. Close those parentheses and then raise it to the 365 times 10 would be 3,650th power. Our account is now worth $7,458.96. That's some pretty good growth after 10 years. Not too bad. All right. There are some problems here for you to try. Good luck.